Let us return back to pointed charge once again. Assume that I have pointed charge Q1 and I have brought another charge Q2 from infinity to a position at a distance r from Q1. We know that Q1 introduces electric potential around it, which equals the magnitude of Q1 over 4 by epsilon naught r. So, the work done to bring another charge Q2 from infinity, where the potential is 0, to this potential point, it would be the magnitude of the tested charge, which is Q2 at the present case, multiplied by the potential at this point. The potential at this point is Q1 over 4 by epsilon naught r. So the work done, or the required work done in this case, or the stored energy in this case between the two charges is 1 over 4 by epsilon naught Q1 multiplied by Q2 over r. If we start the scenario in the opposite, such that Q2 is existing, and we are going to bring Q1 from infinity to the position here, where the position at a distance r from Q2. Q2 introduce a potential around it equals Q2 over 4 by epsilon naught r. And the work done to bring Q1 from infinity to this point, it would equal the magnitude of Q1 as the tested charge multiplied by the potential at this point. So it would be Q1 multiplied by Q2 over 4 by epsilon naught r. So if I started with Q1 and bring Q2, or if I started Q2 and bring Q1, but at the end Q1 and Q2 at a distance r between them, the stored energy in this system, it would be 1 over 4 by epsilon naught Q1 Q2 over r. Okay, that's what we are seeing. The electric potential energy of the system of charged particles is equal to work needed to assemble the system with the particle initially at rest and infinity distance, so from the other. For two particles the separation, the stored energy U, or the work done, is 1 over 4 by epsilon naught Q1 Q2 over r. The question now, we have already allocated Q1 and Q2 in their positions, and we are planning to bring another charge Q3 from infinity to another point, for example here. So the work done to bring the pointed charge Q3 from infinity to a point here, it would be the magnitude of the charge Q3 multiplied by the potential due to Q2 plus the magnitude of the charge Q3 multiplied by the potential of Q1. So that's what we are seeing. If I have already Q1 and Q2 and I'm going to bring Q3, so in this case Q3 has a potential due to the presence of Q1 and another potential due to the presence of Q2. Let us build a system of charge starting with one charge Q1 in place and others are infinity. Then we bring another one, say Q2, from infinity and put it in the place. The potential U12, the potential between 1 and 2, is 1 over 4 by epsilon naught Q1 Q2 over D, associated with the pair of Q1 and Q2. Now, let us bring the third charge Q3 from infinity. If we bring Q3 from infinity, where the potential is 0, to a point here in the field of Q2 and Q1, there will be a potential due to Q1 equals Q1 over 4 by epsilon naught D here, where D is a distance here. This potential will be multiplied by the value of Q3 to obtain the work done to move Q3 from infinity to this point. On the other hand, we have another potential from Q2 at this point, and this potential is Q2 over 4 by epsilon naught D, And this potential multiplied by the value of Q3 will correspond to the work done to move Q3 from infinity to this point due to the potential of Q2. So the required work to allocate the point to Q3 at this point is effectively the work from 1 to 3 plus the work from 2 to 3, or the stored energy at this point is the stored energy from 1 to 3 plus the stored energy from 2 to 3, which is 1 over 4 by epsilon naught Q1 over D. This is the potential of Q1 at this point, multiplied by the magnitude of the charge Q3, plus 1 over 4 by epsilon naught Q2 over D, which is the potential from Q2 at this point, multiplied by the magnitude of Q3. Now this is the stored energy due to moving Q3 to this point. And previously, we have the stored energy to move Q2 from infinity to this position. So the total stored energy inside this system is effectively the summation of the potential between Q1 and Q2, Q1 and Q3, Q2 and Q3. So the total stored energy in this system is the stored energy between 1 and 2, and the stored energy between 1 and 3, and the stored energy between 2 and 3. So it is simply 1 over 4 by epsilon naught Q1 Q2 over D plus 1 over epsilon by 4 by epsilon naught Q1 Q3 over D plus 1 over 4 by epsilon naught Q2 Q3 over D. So the total potential energy of the three charge system is the sum of the potential energy associated with the three pairs of the charges. This sum, which is actually independent of the order, such that assume that I've started with Q3, then I have brought Q1 from infinity to this point. So the energy or the stored energy between 1 and 3, it would be U13. Then if I have brought Q2 from infinity to this position, so the stored energy between 1 and 2, it would be U12, and between 2 and 3, it would be U23. So now I have started from 3. If I'm started from 2, and I have brought Q3 at the beginning, so the first energy I have done, or the first work I have done, is U23. Then if I have brought Q1 from infinity, the work done, it would be U12 plus U13. So the summation of the total stored energy in a system of charge is the same regardless how this charge has been allocated at their points. So the sum, which is actually independent of the order which the charges have brought together, is this value. Okay? From this we can conclude that the electric potential energy of a system of charged particles, the total potential energy of a system of charged particles is equal to the work applied. Force must be assembled to the system starting with the particles from infinity part away. Calculate the potential energy of a pair of charged particles. If a system has more than 2 charged particles, then the system's total potential energy is the sum of the potential energy of every pair of these particles. Alright? As a numerical example, assume that we have 3 charges Q1, Q2, and Q3 are separated by equal distance d, and Q1 has a positive charge, positive Q, Q2 is negative charge, negative 4Q, and Q4 is positive Q, and the value of D is 12 centimeters, and the value of Q is 150 nanocoulomb, and it is required to find out the total energy stored in this system of a charge. So the figure shows 3 charged particles held in fixed position by forces that are not shown. What is the electric potential energy? What is the stored electric potential energy of this system U of this charge? So we say that the total stored energy is the stored energy between 1 and 2 plus the stored energy between 1 and 3 plus the stored energy between 2 and 3. So it will be 1 over 4 by epsilon 1 and 2 Q1 multiplied by Q2 over D Q1 is positive Q, Q2 is minus 4Q. U13, Q1, Q3 is positive Q multiplied by positive 2Q over D. We actually can take D as a common factor because the distance D is the same. Okay. U23 is Q2, which is minus 4Q multiplied by plus 2Q over D. By taking this summation, it is simply 10Q squared over 4 by epsilon naught D. This is minus 4 plus 2. Yeah, minus. This is minus 4 plus 2. It would be minus 2. Minus 2 minus 8 would be minus 10Q squared over 4 by epsilon naught D. By taking this, 1 over 4 by epsilon naught is 8.99 multiplied by 10 to the power 9. 10, the value of Q is 150 nanocoulombs. 150 multiplied by 10 to the power minus 9 coulomb over D. And as I mentioned before, the distance should be in meters. So we are going to convert centimeters into meters. It would be 0.12 meters. By calculating this, the stored energy, it is negative 1.7 multiplied by 10 to the power minus 2 joules. Or in other words, it is minus 17 millijoules. The minus sign, it means that if the force which holding this charge has been released, the charge will be attracted to each other. So effectively, I'm holding a force to make them away from each other. That's why the stored energy is negative. If the stored energy is positive, it means that if I have released the force, they will be going away from each other. Okay, all right.